Good morning, everyone. Welcome to All Things Open AI, the inaugural conference. Welcome to the Builders track specifically. My name is Don Shin. I'm the founder and CEO of Crosscom, the sponsor for this track. We're an emerging technology consultancy located right here in downtown Durham. I've been running the company for almost 30 years now. And I will say, over this career of 30 years, I will say that the possibilities and capabilities represented by machine learning and Gen AI are proving to be the most life-changing, impactful in my lifetime. No exaggeration. I think we are all here because we agree on that. And I think with the greater amount of impact, the greater the need for open source, so that our future, our collective future, not just as software developers, but really as a species, as the human race, is not just controlled by a handful, but really is a collaborative future shared by all of us. And that's why we're sponsoring this conference, because we are super excited, passionate fans of open source to make sure that this technology is impactful and accessible for all. You're going to hear from a whole bunch of pioneers and experts in this space that are crafting our future together. So super excited to be opening up this track. For our first talk, large language models are transforming industries, but let's be honest, fine-tuning them can feel like a privilege reserved for tech giants with deep pockets. What if there was a way to level the playing field? And today's session is all about that, unlocking the power of large language model fine-tuning without breaking the bank using open source machine learning orchestration. Our speaker, Shivay Lamba, is no stranger to pushing the boundaries of machine learning and DevOps. At Couchbase, he's helping developers harness generative AI with vector search. He's a contributor for open source projects like Kubeflow and Flyte, and he's also a mentor, an open source advocate, and has shared his experience at conferences around the world, from GitHub Satellite to TensorFlow.js Show and Tell. If you're looking to make large language models more accessible and cost effective, you're in the right place. Please welcome Shivay Lamba.
I hope everyone is able to hear me. Okay, I'll not take a lot of time because I know everyone is super excited for this conference, and I'm just incredibly blessed to be part of this incredible group of speakers and attendees. I had my chance to visit All Things Open back in 2022, and this brand of conferences being organized by Todd and all the other folks, I think it's a blessing for all of us to be in this kind of a group, because everyone is super passionate about AI and about open source, and it's a celebration of bringing together now all those things within open source with AI. So I'm Shivay. I come all the way from New Delhi, so I'm extremely grateful for to the conference and my company for being able to support my travel all the way. As you might know, that traveling 20 hours is not going to be very cheap, so extremely grateful to them. But yeah, today we are going to be talking more about fine-tuning large language models and how you can do that in a more cost-effective manner, right? Because as we know that these models are not just simple, operation like a 2 + 2 mathematical operation. They have a lot of internal architecture that involves multiple sets of different types of models, and sometimes even training these can take months at a time. So we don't see like a GPT-4o, or if you talk more from an open source perspective, like recently we just had the Gemma 3 models that were launched, which are these models from Google, which are having open weights. So they don't just release these models every few days, right? It takes them a significant amount of time to be able to release new architectures. So how do you do it in a more cost-effective manner, such that, as during the MC we mentioned, we can make it more accessible to even individuals or companies who might not have a lot of compute to harness 10,000 GPUs at the same time, because as we know that GPU compute is one of the most expensive things. So that's what my main focus will be from today's session, and of course I'll be here throughout the entire day. If you have any questions around my session or just around large language models, I'll be more than happy to answer some questions. So what we're going to be covering today, first kind of a basic primer on why to actually fine-tune large language models. Then we'll look at some of the strategies of how do you actually do that, and specifically talk more about this approach towards declarative machine learning, right? And we'll touch upon that in a bit, because this is more of a design paradigm when it comes to actually being able to like run not just like run inference for machine learning models, but also training, fine tuning. It's more of a design paradigm that of course is more opinionated, so some of you might not agree with it, some of you might say that yeah, this is the perfect solution that we need. But my perspective is to just make all of you aware about this particular design paradigm when it comes to fine tuning models, but it's not like the one solution to all of the different kind of capabilities that might be possible. And finally, we'll talk about how you can fine tune these models with the help of Flyte, which is an open source machine learning framework that is currently under the Linux Foundation. So first, let's just talk about fine-tuning LLMs, right? And of course, this we don't need any other introduction, because if you were there yesterday, there are so many sessions around retrieval augmented generation, large language models that of course everyone knows. Or if you don't know, then just a basic primer. You take a set of inputs. These are tokens, and then your LLM understands these input tokens and generates a set of output tokens based on its own knowledge base that it has been trained upon. Now, of course, more often than not, if you're dealing with proprietary data, most of these LLMs will not have access to that information. So that's where we get to see that they either hallucinate, and because of the non-deterministic nature of these particular models, you often need to employ techniques like prompt engineering, where you give a prompt. You just don't ask, okay, what's the capital, or probably a better example would be, what's the schedule like for all things open? Now, because we haven't given enough context, the AI model might just randomly give you the schedule for the year of 2021 for all things open, or 22. So you give it more specific input, and you also give it examples of how the output should look like, so that if you want to get consistent results from the LLM, you can give it that specific instruction that, hey, this is the type of questions that I'm going to be asking you, and these are the set of answers or the format of the answers that I expect. So while this is great to be able to derive better results from these large language models, it's still not useful, especially if you are trying to access information from an LLM on which it has not been trained upon. So that is why we come across techniques like fine-tuning or even retrieval augmented generation. These are the two different kind of techniques that you'll always hear, and probably you'll get into a debate, which one should I pick? Now, this particular talk is not to kind of differentiate between them, but I'll like to focus more on fine-tuning. So in a nutshell, the easiest way to kind of understand what fine-tuning means is that when you want your large language model to be hyper specialized on a particular type of task. So of course, we know that these LLMs are very general purpose machines. They can, do a bunch of different tasks like summarization. Of course, these days they can also generate text or images, videos, right? But if we want them to be hyper specialized on a particular type of task that you're trying to do, right? It could be generating an email for your boss, and you want it to be like the perfect. Then what you'll do is that you would take a small set of data, and you would retrain the weights of these models to be more optimized for these specific tasks. And the way that this happens is that, as you know, that these foundations of these large language models are based on deep learning models, right? And most of these deep learning models will have weights and biases. So essentially, when you train a deep learning model, you're training these weights over your labeled data. So once you have used them and you have the LLM ready, now you'll prepare a set of input prompts and the output that you expect. And now you will retrain certain weights of the LLM, not all. So we are not saying we are going to be doing retraining. Fine-tuning would just take a few of the layers of your weights, and you would retrain them over this new data set that you have prepared. And based on the data set, right, so essentially what would happen is that these weights would look at their current response that they generate and the expected response. And that's your error. And they would be optimized, and we'll run a set of optimization techniques to reduce that error between the expected value and the given value that I've given in your fine-tuning data set. And this way, over time, when you run it over a number of different epochs or training cycles, over the duration of time, these weights will be more optimized for this hyper-selected set of your input data set that you are used for fine-tuning. So as we said that fine-tuning is updating the model weights over a specific data distribution so that your distribution graph of your data then leans towards your fine-tuned data set. So again, this is quite a complex flowchart, but kind of gives you a perspective that, for example, if you're looking for data privacy, of course, that means that your LLM should work on your private data. You would use fine-tuning instead of prompt engineering. And then, of course, if you have machine learning skills, then you can use more advanced fine-tuning systems. Or if you don't have machine learning experience, then perhaps you can use some of the low-code fine-tuning materials, right? And today, because fine-tuning as a concept is well known, there are platforms that give you UI like Nebius AI Studio that can give you like just general UI elements from where you can just fine-tune, or if you want to do it through programmatically, then you can do that with the help of Python and different other open source libraries like Flyte. And then finally, like if you get the result, you go ahead and you ship your project. So the next part of my presentation is how to fine-tune these models. Now, I like to categorize these, or of course the general consensus around the machine learning ecosystem is to essentially divide these into three different main categories, right? The first one is continuous pre-training, and then the next one is supervised fine-tuning, and finally we have RLHF, which is reinforcement learning from human feedback. Now, for today's particular session, because it's just 30 minutes, I would focus on the middle one, which is the supervised fine-tuning, and that's the most popular technique for fine-tuning your LLMs. But just to kind of give you a bit of background around CPT, or the continuous pre-training, it's essentially continuing the process of training your model, but you just add a few additional tokens of dataset which are from your dataset for fine-tuning your model, and that allows you to just adjust the model weights and enhance the capability of the model to work well with your private dataset. But what we'll specifically focus on today is going to be the supervised fine-tuning, where we take an existing fine-tuned model, and as I mentioned earlier, that we will prepare a set of input and output prompts, and we'll now just expose this existing model and fine-tune it just a few of the weights that are relevant for our use case, and we will go ahead and execute it. So this way, what we enable to do is that this particular process of just adjusting a few of the weights is a lot more cost effective as compared to completely retraining of your model, which will require a lot of GPUs, or probably a cluster of GPUs. And trust me, like even fine-tuning is not something that you can just do off the fly. It still requires a significant amount of compute resources, but it's a lot lesser than completely fine-tuning, completely retraining your model from scratch. And finally, we have RLHF, which kind of takes feedback from humans. So we continuously ask the human to provide their feedback, and we enhance the capability of the model. But for this purpose of this talk, we will just focus on the supervised, or the SFT. Now, of course, if we touch upon some of the core principles for just training large language models, right? And the reason I want to pick up on this is that we will use some of these inspiration or learning techniques to also then see how it works for fine-tuning. So the specific one that I would like to probably touch upon is this model parallelism. So the idea is very simple. You take an original machine learning model and you break it into different weights, and then you train these different weights on different GPUs, and then once these weights have been trained, you combine them using what we call as back propagation, and you get your combined model. So rather than trying to load a very large model on a single GPU, which might not be the most efficient, you break down your model into different weights, and you can now use a cluster of different GPUs and train these separate weights at the same time. So this is typically the process for training your machine learning models. And similarly, you can also use something called as data parallelism, where you have like different GPU machines and you have divided your data set into different parts, and then you can repurpose parts of your data set and train them on different GPUs. So this is again more of an optimization technique on a hardware level, which is commonly employed. It's used by most companies around the world, like OpenAI, Google, Microsoft. I mean, these are industry standard techniques that are used for training. But we'll now see that how do we reuse these techniques for fine-tuning by looking at some of the different techniques for fine-tuning models. So the first one is called as zero redundancy optimization. So this particular technique is part of an open source library in Python called as deep speed. And deep speed is a technique that is used to optimize and enhance the capabilities of large language models. So here what we are doing is that we are employing those similar techniques that we saw with training of the models, with the model parallelism and data parallelism, such that we will shard our model weights and across different workers. So in this case, these workers will be GPU nodes in a distributed environment, which also then makes the fine-tuning process way faster, but it just makes it much more optimized, right? So that's zero redundancy optimization. Now, some of the more industry standard techniques is quantization. So as we know that whenever you talk about machine learning models, we are usually talking about precision. And this precision comes from the fact that how much accurate these models are, or how much data that these models can basically store. So the idea is that when you have larger models, they'll have more precision. You try to reduce the memory requirements of your models, and that means there is a certain trade-off in the precision because the model will be able to occupy lesser space. But we try to do it in a way that this handoff is, of course, forward-leaning. That means that the precision that is being lost is not that much. So we are still, and we are having some additional optimization techniques that can help retain that precision level. So usually this is great if you want to like fit larger models into your standard GPUs, because larger models might require you to use a cluster of GPUs, but by reducing their footprint, you can fit them and train them on a single or a couple of GPUs. So this way you don't need to use multi-data of GPUs. You can bring down the number of GPUs that you might need for this fine-tuning. And another, one of the most commonly used techniques for fine-tuning is what we call as LoRa, or low-rank adaptation. So idea here is very similar, that we try to identify what are those specific weights in my model, in my LLM, which are relevant for my data set. And then once I've been able to apply or understand those specific weights, then I'll just go ahead and fine-tune those particular models. Now, the great thing about LoRa is that you can actually also combine this with some of the other fine-tuning techniques like quantization. So if you are in this space, you will probably hear about 8-bit quantization, or QLoRa, which is quantized LoRa, where you not only reduce the size of the models by reducing the precision, but you also then apply the technique of LoRa, where you identify those specific weights and then you fine-tune the model over different epochs. So this way you not only get a much more smaller model, but then these models have been trained upon those specific data sets or instruction sets that is very specific to the task that you're being used. And this is the different change that we have, or the definitive change that we have seen, because models are becoming more optimized. As you might have seen, like DeepSeek, it just blew off the water in terms of the cost. Like, it is super cheap to run. And a lot of this is because these models are becoming hyper specialized at running specific tasks. And that is the way to go if you are trying to make more optimized workloads. This is just comes from the fact, from my personal learnings, that of course there's a separate discussion about SLMs, which are small language models. But if you're specifically talking about large language models, you want them to be hyper specialized on specific tasks, and this makes their execution a lot more efficient, right? That's just something that you can approach in your own companies. But coming to the most important aspect, so of course, fine-tuning, or we talk about retraining, these techniques are expensive. And a lot of us come from backgrounds where if you are SREs or DevOps engineers, you might not have worked with a lot of GPUs or AI systems, and your cost of running these models can very quickly skyrocket, and that's what we want to prevent. And that's why we want to talk about declarative machine learning orchestration. So orchestrators, right? They are this logical flow of compute that helps you to take your data from your input state to a desired state. And the way that we typically do this is with the help of directed acyclic graphs. So the idea is that you take a process and you break it down into different components. And each and every component is interlinked with each other, and you can run each and every component, or what we also call as like a task, separately, and you can also then very easily, if you want to scale up certain aspects of this task, you can do that. And machine learning is perfect match for orchestrators, because as we know that when we talk about like even fine tuning, it's not just one process, right? Before fine tuning, you had the training. Before training, you had the data prep. So when we talk about like machine learning lifecycle, there are different components. So you can very easily fit in a typical machine learning lifecycle with the help of an orchestrator. And that is why, because of the fact that these orchestrators are very much relevant for being able to optimize your workflow, they also give you a lot more additional things, such as the amount of compute that you're using per task in your workload, or how the data basically flows between these different tasks. When we talk about, like, let's say a machine learning task, if you want to maintain type safety between the different tasks, you can basically do that with the help of orchestrators. And what are the resources? And like, this is the most important, like, what is the amount of resources that you need per task, right? And I would really want to touch upon this last point, and I'll show it in more detail as we go deeper into this particular session. So, and also just want to be cognizant of the time. So we have around 10 minutes, that's good. So I'll officially now introduce you to Flyte, which is a production grade orchestrator that has been optimized for data and machine learning workloads. And if you're running a lot of analytics, or you're running a lot of data pipelines, then Flyte is a really good tool that you can leverage. It's currently under the Linux Foundation. It has close to 6,000 GitHub stars, and it's being used by companies like Lyft, Spotify for their recommendation engine. So, a lot of big companies are already adopting Flyte as an open source project for their ML workloads. So the crux of what basically happens in Flyte is that at the core, Flyte has been built on top of Kubernetes. And of course, as we know, that Kubernetes is probably the ultimate orchestration platform for building distributed compute. So the idea is that you define these tasks, and these tasks correlate to the different parts of your machine learning cycle. So there will be a task for pre-training, there will be a task for data collection, there will be a task for fine-tuning. And all of these tasks then can be logically grouped with the help of workflows, and then you execute these workflows inside of your Flyte cluster. And of course, because this is built on top of Kubernetes, your workflows will run in designated pods, where you can also then assign CPUs or GPUs by defining the YAML files. And there are inherent a lot of different other benefits that you get with this. That's more on if you want like a really hyper specialized multi-tenant environment, where you want differentiation between your dev environments, production environments, that are all thanks to the RBAC capabilities of Kubernetes. So task, as I mentioned, is the building block of an orchestrator in this case, and not just like for Flyte, but in the case of any orchestrator platform that you might use, like Airflow, task is the basic building block. So example in a machine learning cycle would be just a task for collection of your data. And as I mentioned, workflow is composition of different tasks together. So if I say that I want to create a workflow for fine-tuning, that would basically mean that I'll first prepare my fine-tuning dataset, and then I'll bring in my model and I'll fine-tune it. So there'll be like 2 to 3 different tasks that are logically grouped together. And the idea here is that you can also then divide your models into different domains. So domains is like, if you want segregation of your development environment versus production environment, you can do that very easily. Then you also get type safety out of the box. So you can define the format of your tasks, whether it's like a data frame or if it's like of the type model, if you are like using it for fine tuning. But the most important aspect here is the declarative infrastructure, right? So I've been talking about declaration. And the core principle here is that usually, and this is a common mistake that most companies basically do, that they say, okay, they've heard that LLMs require a lot of GPUs, so they will literally just push 20 different GPUs at the same time and utilize all of them at the same time to do the fine-tuning, which is absolutely not required, right? Because imagine running 20 GPUs at the same time, where if you're running like an NVIDIA H100, I think the cost of running it is around $40 per hour. And I might be wrong. It might be even higher. I'm just making a rough estimate. So you can very easily bring up your cloud costs into thousands of dollars within a few days. And I have been at that receiving end because I was doing a lot of retraining of models in a past life as a software engineer. So I can, speak to that, like the cloud cost can really skyrocket. So idea here is that what we are trying to do is, as we know that probably data collection does not require you to have a lot of compute. So you can selectively mention that for that particular task, I only want to allocate a CPU. Then for fine tuning, I only want to allocate a collection of CPU and GPU. And when you define this with declaratively, and I'll also show you a code sample in a bit, you're able to, of course, make your optimization of the usage of your hardware much more. And because you're optimizing the usage of your resources, it will inherently also help you optimize your costs, because you're being very selective on what are the parts of your machine learning workload where you want to use very specific resources. And specifically, since this is working under the hood with Kubernetes, you're using some of the techniques in Kubernetes, such as your GPU scheduling or sharding of your GPUs for more optimized retraining of your models. So going a bit further into like how you will fine tune these LLMs with Flyte. I know we are kind of roughly on time. So in the last 5 minutes, I'll quickly show you how this looks like with the help of a code sample. So for that, I'll show you a demo of a supervised fine tuning example with the help of Flyte. Now I do have a GitHub or a code space. Oh no, sorry. This is a collab, Google Collab notebook. So here, I'll quickly show you like my training pipeline. So here, of course, as I mentioned, that you define different tasks. So I have defined a workflow for my training pipeline. And here, you'll see that I have defined the different tasks that I'll be using. So for that, let me go over to specifically to my task for training or the model. So here you'll see that I have these tasks, and whenever you define a task, it's like a Python annotation, right? So you define the task and you basically also mention that for that particular task, what are the ephemeral resources that you need? And these ephemeral resources come from the stateless architecture of your Kubernetes. So here you define that you want 2 CPUs and 1 GPU, right? But for example, if you want to just download a model, you don't need a GPU at that time. So you can just define that you just need 2 CPUs. And now, for example, when it comes to training of the model, you do want a CPU and a GPU, right? So this way of being able to get granular control over what aspects of your cluster or what aspects of your pipeline you want to give access to GPUs or CPUs. So this is where you can make these optimizations. Now I'll also just quickly show you an example of a running project that I did. So here what I basically did was I ran a tutorial on how you can fine tune a BERT model, which is a NLP based large language model. So here what I did was that I authenticate with my serverless environment. So Flyte, you can run it on Docker, or you can also run it on a platform called as Union AI, which is like a SaaS built on top of Flyte. So here I'm just logging into the serverless environment from Union, and I'm creating a simple workflow for the BERT pipeline. And this pipeline step is what I just showed you, which basically involves me downloading the BERT model, and then I'm retraining or fine-tuning that model over a custom dataset that I have downloaded from Hugging Face, and then I go ahead and I evaluate that particular model. So this way I run this workflow, and just to kind of give you a UI or GUI of how this execution basically looks like. So let's look at the execution that we ran for our training pipeline. So here you'll see, if you look at the the DAG pipeline. So here you'll see that we started, and then we have these 2 different tasks that are downloading this particular model. Then we run the specific task for training of the model, and then finally we visualize our data set, we evaluate the model whether it's running perfectly fine or not. And then if you want to run batch predictions, you can do that automatically. And the great thing is that you can scale up individual parts of these models based on the requirement of the user, right? So this is like a perfect example to kind of give you an idea that how you can re-visualize your machine learning pipelines with the help of these these DAG pipelines. And now you can also enable parallelism. You can define the ephemeral resources that you need per task, and inherently this will help you with making your machine learning workloads more optimized and your fine-tuning more optimized by giving that granular control, right? So in case you need help with any resources, this is a good slide where you can look at the Flyte project, and I also have some specific notebooks that go deeper into like how do you do quantization, how do you do LoRa fine-tuning. But of course, today's talk was not like a deep dive into fine-tuning, but more about how do you make fine-tuning more effective, right? And again, just a disclaimer that this is not just one single technique. There are multitude of different techniques, but I wanted to kind of portray my vision, or a general, like, an alternative vision towards how do you make more efficient usage of your hardware resources when it comes to fine-tuning. So I hope that with today's talk, you were able to get those insights. And, of course, I am probably over time for the summary, but we covered, the main difference between prompt engineering and fine-tuning. And then we spoke about different types of fine-tuning, and the general consensus is that depending on your use case, you might find one or the other fine-tuning technique which will be more relevant. So this question, okay, which fine-tuning should I choose? My simple answer is that depends on your use case, right? Depends on the amount of resources that you have and how much reduction in the quality of the model you want as compared to how efficiently you want it to run. But yeah, with that, thank you so much. You can connect with me on my Twitter or X or on LinkedIn at Shivay Lamba. And I'll be really happy if you can share your learnings from this session. You have been taking some slides and some screenshots. So post about it, tag All Things Open, because this is the first iteration of this conference and we want it to be a massive success. So share about your learnings with others who could not unfortunately join us. In fact, who could also not join us in this room. I know it's a small room, but it is good to see so many people excited to try to sit on the stairs. But do share it with them, and I'll be around for the event for answering any questions. Thank you so much. Fine, I would like to take a selfie with everyone. That's something that I do, if everyone is fine with that.